So let us now give a very nice characterization of relative extrema using the derivative. We say that a function f over some interval I into the real numbers is increasing if f at x1 is smaller than or equal f at x2 for every x1 smaller than or equal to x. It is similarly decreasing f at x1 is greater than f at x2 for every one equal. And you remember this from calculus, but also looking at it, here's an increasing function, f at x1, f at x2, f at x1 is smaller than f at x2, and it's decreasing the other way. Notice here, of course, the way I drew it, I assume these functions to be continuous, and I make absolutely no mention of the derivative of the function. Just talking about a function which may or may not have a derivative. Increasingness, decreasingness, as characteristics of a function, those exist even if function is not. Now, if these inequalities here are strict, then we're talking about functions which are strictly increasing, strictly decreasing. This is the function equivalent of sequences that are monotone. Monotone increasing, monotone decreasing. Function that is either increasing over its whole domain or decreasing over its whole domain, but we might not necessarily know which one of the two it is. We say that it is monotone. We might have strictly monotone if the increase or decrease is strict. Well, when it does turn out that the function is both continuous and differentiable, then there is a link between increasing, decreasing, and the sign of the first derivative. So you have some function from AB to the R, from AB to the real numbers R. It is continuous on the interval AB and differentiable the open interval AB. Then you conclude f is increasing on AB if and only if f prime at x greater or equal to 0. How we prove this? There are two directions to prove. Let's start by assuming that f is increasing. We'll pick some point C in the open interval AB for every x which is not equal to C. In the interval AB, the difference quotient here, f at x minus f at c divided by x minus c is thus greater than or equal to 0. That's the case because f is increasing. Clarify what this means. Rather, make sure you understand what this means. The function is increasing, f at x is smaller than f at x1 is smaller than f at x2 when x1 is smaller than x2. So here we've picked our value c somewhere in AB because the function is increasing. Either x is smaller than c, in which case f at x is smaller than f at c, in which case this quotient here is non-negative, or if x is greater than c, and c is smaller than x, which means that f at c is smaller than f at x, but then, yet again, the quotient is non-negative. This is true since f at x greater than f at c, greater than c, c f is right. But we know that f prime at c exists because by assumption the function is differentiable on A. And we know what the definition or the value should be. It's going to be the limit x goes to c, this one. We know this limit exists because c being in the open interval AB is by necessity a limit point. This limit makes sense, x going to c. By the analog of by one of the properties of the limits, this means derivative has to be greater than or equal to each of these terms here is greater than or equal to 0, no matter where you are in the interval AB, and the limit of these terms has to be greater than or equal to 0. But we've proved one direction, but the other direction. You assume f prime positive for every value of x, the open interval pick two values that are pick two values, x1, x2, which are smaller. Pick two values, x1 and x2, x1 being smaller than x2, both of them in the interval AB. By the mean value theorem, you can find a point C between x1 and x2, such that f at x2 minus f at x1 is equal to f prime at C. Mind you what this said. This is x1, this is x2. Function is differentiable. There's got to be some point C where the tangent line C has the same slope as the slope of the secant line joining the two endpoints of the curve. Now, I speak of slopes here because, look, we have a continuous function. That's the one I drew. But in practice, the mean value theorem isn't just about slopes. It's about derivatives and endpoints. Now, we know f prime at C is greater than 0 because f prime is positive over the whole interval AB. We know x2 is greater than x1, and so f at x2 minus f at x1 divided by x2 minus x1, that's equal to f prime at C, but f prime at C is positive, so f at x2 minus f at x1 divided by x2 minus x1 is greater than 0. It's non-negative. Since this is positive, the only way for this ratio to be positive for x2 greater than, well, we picked x1 and x2 arbitrarily. We didn't specify which ones they were. We just said, let's assume that x1 is smaller than x2. Concluded, using the hypothesis that f prime was greater than or equal to 0, that f at x2 had to be greater than or equal to f1, which is to say, f increasing on the interval. It's not too difficult for you to see. It's not too difficult for you to see that there is a corresponding result for decreasing functions. The derivative over these intervals have to be. Now, note for you, if you use strict increasing or strict decreasing, the theorem is not an if and only if result in one of the directions is not valid. Can you find which one?